This is lecture 3A, and today we're going to start the topic of thermodynamics, specifically the properties of entropy and free energy. Thermodynamics studies the energy of a system, and then how much work a system could produce, and then how to predict the spontaneous change a system will undergo. And so one of the most important properties of thermodynamics is the amount of energy in a particular system, and we call that its internal energy, abbreviated by the letter E. It's the total energy of a system. This could actually be the reactants in a chemical reaction. It could be a car, whatever you want to define as your system. And what we found is that any time a system undergoes a type of change, it can absorb or release energy, but when it does, energy is always conserved. Energy is conserved during all processes. In 1847, Hermann von Helmholtz presented a mathematical argument for this concept, which was known as the law of conservation of energy. And today we call this the first law of thermodynamics. And Helmholtz stated that the change in energy of a system is equal to the heat that enters the system plus the work done on the system. This first law is quite often expressed algebraically in this form: delta E equals Q plus W. Delta E means the amount of internal energy that a system changes when it undergoes some process. The Q in the equation stands for heat. So a lowercase q stands for the heat, and that is just any energy transferred that causes a temperature change. So if a chemical reaction occurs, and the surroundings, the test tube that the reaction is in, warms up, that's a temperature change. So the reaction has transferred heat energy to the solution. If you have a chemical reaction in the test tube, and then when the reaction occurs, the water in the test tube gets colder, then heat energy has been transferred from the water to make the reaction occur. Also an example of heat transfer, this time from the surroundings to the reactants itself. Then the other term in the equation is W. That stands for work. That's any energy that gets transferred during some process that causes an object to move. So for example, if a gas is produced and it's in a balloon and the balloon starts to expand, then that's actually work being done. Now, a particularly important concept in thermodynamics is the idea of a state function. A state function is any thermodynamic property of a system whose change can be determined by only knowing its initial and final states. Doesn't matter the pathway in which that change occurs. And it turns out that internal energy is a state function, which means that if you ever calculate the change in internal energy, the delta E, that value is always going to be independent of the pathway of the change. And if we apply that to a chemical reaction, let's say we're going to react hydrogen sulfide with zinc ions, and it's going to react and turn into zinc sulfide and hydrogen ions. And we want to determine what the change in internal energy is for this particular process. In my graph, I have energy graphed on the y-axis, and as you go from left to right, the reaction proceeds from reactants to products. The molecules of hydrogen sulfide and the ions of zinc have some energy inherent in them. When they turn into the product substances, zinc sulfide and hydrogen ions, those chemicals have a certain energy content, and the difference in the energy content of the reactants and the products is what's going to be the change in internal energy. And so because the internal energy is a state function, this delta E value, this change in internal energy, is always going to be the same. Doesn't matter how the hydrogen sulfide and the zinc ions turn into the zinc sulfide and the hydrogen ions. That's what thermodynamics studies. If you know an initial state, the reactants, and you know the final state, the products, what properties can you determine their numerical values for by just knowing where you're starting and where you're ending up? Now, how this reaction actually occurs, what energy profile it goes through, that's a different topic in chemistry. We actually call that kinetics, and that's a topic we're going to discuss later on this semester. But for this particular unit, we're going to be discussing the thermodynamics, which are just properties that we're going to learn that are considered state functions, in which they only depend upon the initial state and the final state, and whatever the difference between that is, always going to be the same value. It's independent of the pathway. Now, a second thermodynamic function that's also a state function is the function called enthalpy. Enthalpy is abbreviated by the letter H, and technically it stands for the internal energy of a system plus the pressure volume product of a system. If we write that out algebraically, enthalpy H will equal the internal energy E plus the product of the system's pressure and volume. We discussed enthalpy back in Chem 1A, but we never actually defined it, at least in my class I didn't. This is the actual definition. Now, we never actually measure a particular thermodynamic property like internal energy or enthalpy. We try to determine how much the internal energy or the enthalpy change. So we're going to want to see how you can calculate the change in enthalpy of a system. And if we want the change in the property of enthalpy, it's going to actually equal the change in the property of internal energy plus the change in the pressure volume product. Now, when you have a change of a product, that's actually the sum of two different terms. It's the sum of the delta P, change in pressure, times constant volume, plus constant pressure multiplied by change in volume. So this is really what the enthalpy change is going to equal. It's going to equal the sum of three consecutive terms. Now, in most chemical reactions that we perform here on Earth, reactions occur on a lab bench or in an open beaker, and the products and reactants are being exposed to a constant external pressure. It's atmospheric pressure here on Earth. So if the external pressure that's being imposed upon a chemical reaction never changes, that means you will not have a change in pressure during most chemical reactions. So in our algebraic description of the enthalpy change in yellow above here, the one term that says delta P times V, that term has to equal 0 because delta P is a value that doesn't change. It's going to be 0. So that simplifies our change in enthalpy. It's actually equal to the change in internal energy plus constant pressure multiplied by the change in volume. Now, with that in mind, let's go back to the first law of thermodynamics that we introduced just a few moments ago. The change in internal energy of a system equals Q plus W. And something back in an earlier thermodynamic chapter that was covered in our textbook concerning heat and work is that if you want to calculate how much work is done by a chemical reaction, it's usually due to the fact that a chemical reaction produces a gas, and the gas expands and pushes against the surroundings, causing work to be done. And we were able to calculate how much work is done by an expanding gas. It's actually negative P delta V. So if I take negative P delta V and put it in place of work in our first law equation, the change in internal energy will have to equal Q plus a negative P delta V. If I solve this for Q by adding P delta V to both sides of the equation, Q, the amount of heat that's absorbed or given off in a chemical reaction or in any process, will equal the change in internal energy plus P delta V. And here's what I want you to notice. The change in enthalpy equals delta E plus P delta V, and Q equals delta E plus P delta V. So that's really significant. Transitive property. That means that delta H, the change in enthalpy of a system, just equals the amount of heat that it gives off or absorbs. So for any chemical reactions that occur at constant pressure, the enthalpy change of a system is always equal to the heat that enters the system. And that's significant because heat is something really easy to measure, especially for a chemical reaction. We do it in devices called calorimeters. So we can calculate how much heat a reaction absorbs or releases. And if we calculate that, that's going to equal the enthalpy change of the reaction. So the delta H of an enthalpy of a reaction will equal the heat gained or lost at constant pressure. And if you ever see a subscript for a particular variable in an expression like Q sub P, that's telling you that the pressure is being held constant. So in situations where the pressure does not change, the enthalpy change will always equal the amount of heat given off or absorbed. Now, how do we calculate the enthalpy change for a reaction? We're going to see if we can come up with a standard enthalpy change for this reaction, which is 4 NH3 gas plus 7 O2 gas yields 4 NO2 gas plus 6 H2O gas. And there's actually 3 ways we can determine what the enthalpy change for this reaction is, because the enthalpy change equals the amount of heat gained or lost by this reaction. If we perform this reaction experimentally in a calorimeter and measure how much heat is given off or absorbed, that value will equal the enthalpy change. So the first way to calculate the enthalpy change for a reaction is experimentally to use a calorimeter, because the Q of the reaction that you calculate from a calorimeter is just going to equal your enthalpy change. We're not going to deal with that this semester. We actually did quite a bit of calorimetry during Chem 1A, but we're going to go to theoretical ways to predict what the enthalpy change for a reaction is going to be. We've actually done these before last semester, but we're going to review it again now. Theoretically, we can calculate the enthalpy change of a reaction by using standard enthalpies of formation, which we'll talk about in a moment. And the third way you can calculate the enthalpy change for a reaction is also theoretically. It can be done using bond energies. So let's go through methods 2 and 3 and show you how you can theoretically calculate the enthalpy change for a reaction, which will therefore equal how much heat that reaction gains or loses as the reaction proceeds. So if you want to use standard enthalpies of formation, these are thermodynamic values that are found on the class handout 5 on our class website. And the data all given on the handout 5 are all data at 298 Kelvin. So technically, you're going to be calculating thermodynamic property values or change in thermodynamic property values at 298 Kelvin. So in this table, you notice here the first column, the heading is delta H naught sub F. So what these are is these are standard enthalpy of formations. Now, thermodynamic data is always tabulated under specific conditions called the standard state. And it's identified with little superscript naught. And that's why you see it says delta H naught in that column there. What does standard state mean? Well, that just specifically says that if you have a gaseous substance, and in fact, all 4 of these substances in this table are all gases, that means that these values are tabulated assuming these gases are at 1 atmosphere pressure. If any of these substances are dissolved in water, we would assume their concentrations are 1 molar. And then if you have any elemental matter, and we have one thing that's elemental here, that's O2, the elemental matter is always in its natural state at room temperature and pressure. So how does oxygen exist at room temperature and room pressure on Earth? It exists as diatomic molecules, and it exists as a gas. So the standard state for an element would be how it's naturally found at room temperature and room pressure on Earth. So what are these delta H naught sub F values that are listed here in the table? Well, these are enthalpy of formations, and they're abbreviated delta H sub F if they're under standard conditions. There's a superscript naught there. But essentially, an enthalpy of formation is the enthalpy change for a formation reaction. Now, what's a formation reaction? It's very similar to a composition reaction. It's when you form the compound from the elements that compose it. So a formation reaction is a reaction that forms 1 mole of any substance from the elements that are composing it. So if we start with the first substance in our table, NH3, what's the formation reaction for NH3? It's the reaction that forms 1 mole of NH3 from the 2 elements that make it up, which are nitrogen and hydrogen. Now, how do nitrogen and hydrogen exist at room temperature and room pressure on Earth? They're both diatomic gases. So the reaction is N2 plus H2 yields NH3. You want to have this equation balanced with a coefficient of 1 in front of the product. So if you're going to have a coefficient of 1 in front of the NH3, that means the only way to balance this will be with fractional coefficients. You will need 1/2 of a mole of diatomic nitrogen and 3/2 of a mole of diatomic hydrogen to form 1 mole of NH3. When this reaction occurs and you produce 1 mole of NH3, the delta H naught sub F value tells you how much heat is given off or absorbed. It says -46, and that means that 46 kilojoules are released when you form 1 mole of NH3. Let's go to the value for NO2. It says 34 kilojoules per mole. That's the amount of heat now that's absorbed because it's a positive number when you form 1 mole of NO2 from the 2 elements composing it. So the reactants are N2 plus O2 because that's how nitrogen and oxygen exist in their standard states. To balance the equation with 1 mole of NO2, we're going to have to use a fractional coefficient in front of the nitrogen. So 1/2 mole of nitrogen gas plus 1 complete mole of oxygen gas will produce 1 mole of nitrogen dioxide gas. And when you form 1 mole of nitrogen dioxide, the value in the table tells how much energy is released or absorbed. Positive 34 means 34 kilojoules are absorbed when 1 mole of NO2 is formed. Oxygen's delta H naught sub F is 0. And that should make sense why that is. What's a formation reaction for oxygen? It's the reaction that forms 1 mole of O2 from the only element making it up in its elemental state, in its standard state, which is O2. So how much energy does it take to make O2 gas turn into O2 gas? It doesn't take any. Nothing happened. So the moral of the story here is if you ever have a substance in your table and it's an element in its standard state, it's going to have a standard heat of formation of 0. And if I had O2 solid or O2 liquid, for example, it would not be a 0 value because that's not standard state. O2 gas is. For the last one, can you predict what the formation reaction would be for gaseous water? It'd be the reaction that forms 1 mole of H2O from the elements that make it up, H2 plus O2. And to balance it, you would need 1/2 mole of O2 to react with 1 full mole of hydrogen gas to produce 1 mole of H2O. So when this reaction occurs and you create 1 mole of water, 242 kilojoules are released during that process. So when you look at your thermodynamic tables, you will see the enthalpy changes of formation for different substances. They're not going to write the reactions out for you, but those are the actual reactions that correspond to these numerical values. And it turns out they don't write the reactions out because you really don't need to see them, because you use those numbers to calculate the enthalpy change of the reaction at the top of the slide by using this simple little algorithm. The delta H naught for any reaction, and we're going to do it for the reaction at the top here, is always going to equal the sum of all the standard heat of formations of the products minus the sum of all the standard heat of formations of the reactants. And when you do this, you have to make sure that when you use a heat of formation of a product or reactant, you multiply it by its coefficient in the balanced equation. So let's see if this makes sense. We start with the products. So the first product is NO2. Now the balanced equation says there's 4 moles of NO2. So I'm going to go 4 moles and I'm going to multiply by the standard heat of formation, or called the standard enthalpy of formation, interchangeable terms. 4 moles multiplied by the standard enthalpy of formation of NO2, which is 34 kilojoules per mole. So in terms of units, you're going 4 moles of NO2 multiplied by 34 kilojoules per mole of NO2. There's one more product. So you're going to add 6 moles of water multiplied by negative 242 kilojoules per mole of water. So we add the standard heat of formations from all the products. And then once we've done the products, we're now going to subtract the standard heat of formations of all the reactants. So now we go to 4 moles of ammonia. I'll go minus 4 moles of ammonia multiplied by negative 46 kilojoules per mole. And there's one more reactant, so I will subtract 7 moles of oxygen multiplied by 0 kilojoules per mole of oxygen. So without having the formation reactions written out, really all you have to do is take the 4 numbers in the table here, and you go products minus reactants, just making sure you multiply each of them by their coefficient in the balanced equation. Now look at each term. I want you to notice what happens to the moles. First term, moles of NO2 cancel out. Second term, moles of H2O cancel out. Third term, moles of NH3 cancel out. Last term, moles of O2 cancel out. So I'm going kilojoules plus kilojoules minus kilojoules minus kilojoules. The answer is just going to come out in kilojoules. All these standard heat of formations were given to the ones column. And so when we add all these together, our answer will go to the ones column. I get negative 1,132 kilojoules. This is a negative number. That means it's an exothermic process. So when this reaction occurs, you actually combust ammonia, then 1,132 kilojoules are released. Now, the amount of energy that's either absorbed or released in a chemical reaction depends upon how much substance you're actually reacting. So we call this an extensive property. It's one that depends upon the amount of chemical change. So it's really hard just to write negative 1,132 kilojoules is the enthalpy change for a reaction, because that doesn't tell anybody, well, how much ammonia did you react? And so usually what they do is they take the enthalpy change for a given reaction and they divide it by the amount of one of the reactants or products. So it's on a per mole or per gram basis. So usually when you do a combustion reaction, you take the amount of kilojoules that are released, you divide it by either the number of grams or the number of moles of the substance that was combusted. And in our reaction, we did our calculation assuming 4 moles of ammonia combusted. So if you divide it by the 4 moles of ammonia, which is a counted number, we'll get a 4 significant figure answer. And so whenever you combust ammonia, the amount of energy released is 283.0 kilojoules per mole of ammonia. Now, this is a really quick way in order to predict enthalpy changes of reaction, and that therefore tells you how much heat is released or absorbed in a reaction. But why does this quick little technique work? Well, it works because of something called Hess's law, and let me show you what that is. Let's say we want to calculate the enthalpy change for the reaction of ammonium nitrate decomposing into dinitrogen monoxide and water. Question is, what's the standard enthalpy change for this reaction? And we're going to actually use the standard enthalpy of formations of our reactant and 2 products, and then go products minus reactants, but I'm going to try to show you why that physically works. So you would have to go to a thermodynamic table and look up the standard enthalpy of formation for ammonium nitrate, which turns out to be negative 365 kilojoules per mole. You would need to look up the standard enthalpy of formation of dinitrogen monoxide, which from our table on our class website is 82 kilojoules per mole, and the standard enthalpy of formation of water, which from our table is negative 242 kilojoules per mole. And what we just saw in our last example is I would just have to go products minus reactants, making sure I multiplied the water by 2, and that would give me the correct answer. So why does that happen? Well, to see how it actually works, we're going to write out each of these formation reactions. Let's start with the ammonium nitrate. The formation reaction for ammonium nitrate would form 1 mole of ammonium nitrate from the elements that make it up, which is nitrogen, N2, hydrogen, H2, and oxygen, O2. There's 3 different elements, right, in the formula of that compound. And to produce 1 mole of ammonium nitrate, you would need 1 mole of N2 because there's 2 moles of nitrogen in the formula. You need 2 moles of diatomic hydrogen because there's 4 moles of hydrogen in the compound, and 3/2 moles of O2 to give you the 3 moles of oxygen in the compound. So this is the reaction whose delta H value is negative 365. Let's do the same thing for N2O. The product is N2O. What is it formed from? Nitrogen and oxygen, N2 plus O2. And in this case, because we only have 1 O in the product, we only need 1/2 mole of oxygen, 1/2 mole of diatomic oxygen on the reactant side. So when this reaction occurs, it absorbs 82 kilojoules. Let's write the formation reaction for water. Water's composed or formed from hydrogen and oxygen, which are both diatomic. And to balance the equation with 1 mole of water being formed, you would need 1/2 mole of oxygen. So when this reaction occurs, it releases 242 kilojoules worth of energy. So what Hess's law is that if you know the delta H values for a series of reactions, and we know 3 of them here, if you can make those 3 reactions add up to the reaction at the very top, then all you have to do is add their delta H's together. So if you look at the reaction given at the very top, we have NH4NO3 as a reactant. And our first formation reaction has NH4NO3 as a product. That reaction is written incorrectly. We have to reverse it. So it goes NH4NO3 yields N2 plus 2H2 plus 3/2 O2. So I'm going to reverse that first reaction so that I put the 1 mole of NH4NO3 on the reactant side. Now, what's the delta H for this reaction? I've reversed it. So if the orange reaction at the top is exothermic by 365 kilojoules, the new white reaction is endothermic by 365 kilojoules. In short, all you do is you change the sign of the delta H if you reverse a reaction. So the delta H of this reaction is positive 365 kilojoules. Now, we've got the NH4NO3 now in its proper spot. Now we have to get 1 mole of N2O on the product side. Our second formation reaction perfectly has 1 mole of N2O on the product side. I'm going to write that formation reaction exactly how it's written. and its delta H value does not change whatsoever. It's going to be positive 82 kilojoules. Finally, I want to get 2 moles of water on the product side. My final formation reaction has water in it, but it's only forming 1 mole of water. I need to form 2. I need to double that third reaction. I need to make it say 2 moles of hydrogen plus 1 mole of oxygen yields 2 moles of water. And because enthalpy is an extensive property, if you're now going to form twice the amount of water, multiplying by 2, you've got to multiply the delta H by 2. You're going to give off twice the amount of energy. So negative 242 multiplied by 2 is negative 484. So now I've tried to arrange the reactants and products in their proper places by taking the formation reactions, reversing them or multiplying, whatever I can do. And now I'm going to try to add these together, and I want you to see what happens. See the N2s? Cancel out. See the 2 H2s? They cancel out. See the 1.5 O2s on both the left and the right? They cancel out. What's left over? NH4NO3 yields N2O plus 2H2O. So these 3 formation reactions, now that they've been adjusted, will add up to make the overall reaction. All I need to do now is add my 3 white enthalpy changes on the very right side, 365, 82, and negative 484. And that's going to give me the standard enthalpy change for this reaction. It comes out negative 37. You would get the same exact answer if you didn't do any of this work. You just went products minus reactants as we did in our last problem. So why does it always work like that? Well, if you notice this reaction here, I've just colored in yellow. That's the reactant in the overall reaction, NH4NO3. I got that from the formation reaction of the reactant, but what did I have to do? I had to reverse it. And whenever you reverse a reaction, what do you do to the delta H? You change its sign, or in other words, you subtract it. So if you're ever going to need to have something on the reactant side, you're always going to have to take its formation reaction and reverse it. In other words, you're going to always have to change the sign or subtract its delta H value. That's why we subtract the heat of formations of the reactants. Now, the other 2 substances I've colored in green here, those are products. They're already on the product side in their formation reaction. I don't reverse them. I just write them exactly how they are. So that's why I add the standard heat of formations of the products, but I do multiply each by a coefficient if I need to. So this is always going to work out. Products minus reactants will wind up giving you the delta H of an overall reaction. So without you having to use Hess's law and write out all the formation reactions, you can just use the simple algorithm, products minus reactants, and we can use standard enthalpy of formations to predict enthalpy changes for chemical reactions. This one comes out negative 37. So we know that when 1 mole of ammonium nitrate decomposes, it's going to be exothermic by 37 kilojoules. Now, let's try to calculate an enthalpy change another way. We're going to calculate the enthalpy change for the reaction N2 plus 2H2 yields N2H4. And I want to do this by using bond energies because that's another way we can predict how much energy or heat is given off or absorbed in a chemical reaction. So we don't have any bond energies listed on the Chem 1B website, but my Chem 1A website, which is, you just go back to the home page, you can get to the Chem 1A website, go to handout 8, and there's going to be bond energies listed on there, and I've got a few of the bond energies listed right here. So how do you use those? Well, you're going to have to be able to draw the Lewis structures for each of the reactants and products to see what kind of bonds there actually are in each of the reactants and products. Let's start with the diatomic nitrogen molecule. My balanced equation has 1 diatomic nitrogen in it, and if you're going to draw a proper Lewis structure, you're going to make sure that all the atoms have 8 electrons in their outer shell. And because a diatomic nitrogen molecule only has 10 valence electrons, 5 from each nitrogen, the only way you can make an octet for each nitrogen is by making a triple bond between the 2 nitrogen atoms. So when this reaction occurs, we're going to have to break a nitrogen-nitrogen triple bond. The balanced equation is reacting 2 diatomic hydrogen molecules. The correct Lewis structure for a diatomic hydrogen molecule is H-H. Hydrogen being in the first row of the periodic table doesn't achieve an octet, it achieves a duet because that fills the first energy level with 2 electrons. So to break a hydrogen molecule apart, you have to break a hydrogen-hydrogen single bond, and there are actually 2 diatomic hydrogen molecules in the balanced equation. So when this reaction occurs, I'm going to have to break 2 different hydrogen-hydrogen single bonds. Now, what am I forming? I'm forming N2H4. The correct number of valence electrons in this molecule should be 14, and if you fill in all the valence electrons and try to make octets for the nitrogens and duets for the hydrogens, you're going to get a Lewis structure that looks like this. So when this molecule gets formed, you're going to form 1 nitrogen-nitrogen single bond, and you're going to form 4 nitrogen-hydrogen single bonds. So how this works is, if you're going to break the bonds in the reacting molecules, you have to use energy to do that. You have to put energy into the system. So that means the system has to absorb the energy, and anytime something absorbs energy, that's an endothermic process, and that's a positive value. So for my nitrogen-nitrogen triple bond, because I have 1 nitrogen-nitrogen triple bond I have to break, and I'm going to consider that a mole of nitrogen-nitrogen triple bonds, I'm going to supply that energy by making it a positive number. Now, I have 2 hydrogen-hydrogen single bonds I have to break. I'll treat those as 2 moles of hydrogen-hydrogen single bonds. And once again, if you're breaking bonds, you have to put energy in. So this is going to be a positive number. So I'm going to add 2 moles multiplied by 432 kilojoules per mole worth of energy. All this energy I've listed so far will break the 3 molecules on the reactant side into individual atoms. Those atoms can then combine to form the one big molecule on the product side. And when molecules are formed and bonds are created, energy is released because the atoms become more stable. So I'm going to form a nitrogen-nitrogen single bond. The energy of that from the table above is 160. So because it's being formed, I'm going to be releasing energy. So I'm going to subtract this to make it a negative number. So minus 1 mole multiplied by 160 kilojoules per mole. And then because the molecule has 4 nitrogen-hydrogen single bonds in it, I'll treat that as 4 moles. I'm going to release, because I'm forming them, 4 moles of nitrogen-hydrogen single bonds, which are 391 kilojoules per mole each. So just by analyzing the bonds that have to be broken from the reactants, which will be positive, and formed in the product, which will be negative, we can add these up and we can calculate the enthalpy change for the reaction. So I've multiplied each of these out, and now if I add it together, this comes out 81 kilojoules. So this means that when this reaction occurs and you form 1 mole of N2H4, that reaction is going to be endothermic by 81 kilojoules. It's going to absorb 81 kilojoules worth of energy. Now, these types of calculations involving enthalpy changes of reactions are actually things we did back in Chem 1A. Now we're going to start to look at some other thermodynamic factors or thermodynamic properties that we haven't learned before. And the first one we're going to talk about was developed in 1865 by Rudolf Clausius. He proposed that whenever some type of process undergoes a change and it changes its internal energy, how does it change its internal energy? By either heat or work. Remember, that's the first law. Well, he said that you cannot have your internal energy change by doing all work. Some energy change has to be because heat is gained or lost. So he proposed that there is always some internal energy that cannot be converted into work. Some of it has to be released or absorbed as heat. It turns out that the amount that cannot be converted into work is proportional to temperature. So the higher the temperature change of the process, the more that value is going to be. But this amount of internal energy that cannot be converted into work, he gave a name. He called it entropy. So let's look at a couple of examples, and maybe we can try to determine conceptually what the entropy would be for each of these different situations. Here's a stack of blocks, okay? Now, this stack of blocks has a certain amount of internal energy associated with it. If it undergoes some change, like let's say it falls over, okay, how much of that energy cannot be converted into work? Let's think about it. If you were a mouse sitting here and those blocks fell over and clubbed you on the head, you'd be going, oh my gosh, there was a lot of work done by those blocks. So these blocks can do a lot of damage to a mouse. That means that a large amount of their internal energy can be used for work. So in other words, a low amount cannot be used for work. So therefore, if there's a low amount of energy that cannot be used for work, these blocks have a low entropy, okay? Look at these blocks. They have a certain amount of internal energy. How much of their internal energy can be used for work? If you're a mouse sitting here, are you afraid of those blocks now? No, because those blocks aren't going to hurt you as much. So because these blocks are already really low, they only have a small amount of internal energy that can be used for work. Therefore, they have a high amount that cannot be used for work. So if you have whatever your amount of energy is you cannot use for work, that's your entropy. So therefore, this set of blocks has a high entropy associated with it. Now, notice anything about these two systems? Can we deduce anything about low entropy systems compared to high entropy systems? Well, it looks like the low entropy systems are very organized or ordered, right? And the high entropy systems are very disordered. People recognize that, and they started to realize, oh, systems with low entropy mean order, and systems with high entropy mean disorder. And this led to what we now call the second law of thermodynamics. And that is, in any spontaneous process, which means one that occurs naturally on its own, there is always an increase in total entropy. So if the entropy is going to increase naturally for a spontaneous process, what does it mean if the entropy is increasing? You're going from ordered to disordered. So the amount of disorder increases when a process is spontaneous. So what process do you think would be spontaneous? The blocks on the left turning into the blocks on the right, or the blocks on the right turning into the blocks on the left? It's always going to be this way. The ordered blocks will turn into disordered blocks. So the spontaneous process would be for the blocks to fall, not to spontaneously stack up. And you probably know this is true in your own life. If you have all of your clothes neatly put away in one of your drawers, or your mom puts them away for you, and then you're in there and looking for something, then a few days later, all of a sudden the shirts and the socks and whatever are all mixed up, and it never goes from disordered to ordered. Things naturally always go from ordered to disordered. That's just an example of the second law of thermodynamics. So conceptually, this idea of entropy has to do with order and disorder, but really, what does it mean? And entropy's meaning really was derived mathematically in 1890 by Ludwig Boltzmann, who proposed a statistical meaning for what entropy is. And this is where the symbol S was first introduced for entropy. Boltzmann was able to calculate what the entropy is for a system because entropy is a measure of the number of arrangements available to a system in a given state. And let me show you what I mean by that after we show you his little mathematical expression. He calculated the entropy of the system through this expression here. You will not need to know this one for the test. I will not make you memorize this expression. But Boltzmann's entropy equaled a constant K multiplied by the log of something called W. Let's define each of the terms. So S stands for entropy. K is a constant that we now have named after Boltzmann himself. It's called the Boltzmann constant, which ironically enough, it's just the universal gas constant divided by Avogadro's number. So if you divide those, you're going to get 1.38 times 10 to the minus 23rd joules per molecule Kelvin. And then W is the statistical thing that Boltzmann was able to determine. It's the number of ways that particles can be arranged in a given state while keeping the total energy constant. And let me give you an example of this. We're going to see if we can calculate with Boltzmann's expression the entropy of a sample of gaseous carbon dioxide and then of dry ice, which is solid carbon dioxide. And I'm going to assume that we have a little sample of gaseous carbon dioxide that's only 2 molecules, and then we'll have another sample of solid carbon dioxide, which is again only 2 molecules, and we're going to see if we can calculate their entropies. So on the left is going to be my gaseous carbon dioxide. Now, when a gas is in a container, the molecules can be anywhere in the entire container because gases completely fill whatever the volume is of the container they're in. So I've actually randomly just decided there's going to be 20 possible spots the molecule can be in that first container for the gas. So the first molecule, let's call it the blue one. The blue molecule can be in any one of those 20 spots. Then if we figure out where can the green one be, the green one can be in any spot that the blue one isn't. So if the blue one is in one of the 20 spots, the green one only has 19 other choices. So what are now all the possible arrangements of blue and green molecules? Well, the blue one can be in 20 possible spots. The green can be a 19. If you multiply 20 times 19, you've just figured out every possible arrangement for the blue and green molecules in that container. That's what W is. So to calculate the entropy, we're going to multiply the Boltzmann constant, multiply by the log of W, which is 380. And so we would calculate that the entropy of gaseous carbon dioxide is 3.56 times 10 to the minus 23rd joules per Kelvin. Now in the second container, I'm going to look at a sample of solid carbon dioxide. And in a solid, the molecules aren't flying anywhere they want in the container. They're stuck next to each other as a crystal at the bottom. So these two molecules have to be in these two spots. The blue one has to be in one of the two spots. And then once that one's set, the green molecule has to be in the other. So the W value for the solid would be 2 possible positions for the blue and then only 1 possible position for the green. This multiplies to make a W value of 2. So what's the entropy of the solid? It's 1.38 times 10 to the minus 23rd joules per Kelvin, multiplied by the log of 2, and that comes out 4.15 times 10 to the minus 24th joules per Kelvin. That's a lower value. So who has a higher entropy? Gases have higher entropies than solids. Why would that be? Because they have more possible positions they can be in a particular state, keeping the total energy of the system constant. So for a particular type of matter, the gaseous state always has a higher entropy than the solid state, and in fact, the liquid would be between the two then. So if we think generally about factors that affect the entropy for a specific chemical substance, the most important factor is the state of matter, whether it's a solid, liquid, or gas. And we've sort of seen an example with a gas and a solid, but I'm going to include the liquid now. It turns out that entropies of gases are always greater than entropies of liquids, and then entropies of liquids are always greater than entropies of solids. And the reason for this is, just in our little diagram from before, gases have more possible arrangements than liquids, and liquids would have more possible arrangements than solids. So that means higher entropies. Now, a couple of other factors, a little bit more subtle. If you have substances of different molar masses, they're going to have different entropies. And it turns out the entropy of a large massed substance is always greater than the entropy of a low mass substance. This is something you can memorize if you want. The reason for this is quantum mechanical. It turns out the possible energy states of molecules come from quantum mechanics. And in the quantum mechanical equations where you're solving for the different energy levels, which is E sub I, there is in the denominator of this equation the mass of the particular molecule. So if the molecule's mass is really, really big, that means that as you start putting different I values into this equation to calculate the different energies, they're going to be really, really close to each other. But if the M value is a small number, then the energy differences of the different energy states are going to be a lot larger. So a larger mass means smaller differences in energy levels or closer spacing of energy levels. And so that means the molecules have a more likely chance of being in those multiple different energy states. So therefore, larger masses always give you more possible energy states for the particular molecule, and therefore it's going to be a higher entropy for that reason. Third factor is molecular complexity. And what I mean by this is the number of different elements that make up a particular molecule. The entropy of molecules that have less elements is always less than the entropy of molecules that have more elements, because molecules with different elements allow for more possible arrangements. And let me show you what I mean by this. Let's say we take 2 fluorine atoms and 2 hydrogen atoms, and let's combine them into diatomic molecules. Now, we can either combine them into diatomic fluorine and diatomic hydrogen, which would be molecules that each only contain 1 element, or we can combine them into a pair of HF molecules. And HF molecules have 2 elements in them each. So what would have a greater entropy, an F2 molecule and an H2 molecule, or 2 HF molecules? Well, let's see how many arrangements we can make. If you want to make the fluorines bond together and the hydrogens bond together, this is the only arrangement you can do. Fluorine A would bond to fluorine B, and then hydrogen A would bond to hydrogen B. That's one arrangement, that's all you can have. But if you want to have 2 hydrogen fluoride molecules, you actually have 2 arrangements you can do. You can make hydrogen A and fluorine A bond, and then hydrogen B and fluorine B bond. That's one arrangement. Or You could have hydrogen A and fluorine B bond, hydrogen B and fluorine A bond, two different arrangements. So the fact that molecules have more elements in them always allow for more possible arrangements. That means their entropies are going to be higher. So let's see if these three different factors make sense to you. Let's see if we can explain each difference in absolute entropy. Why would diatomic chlorine gas have a higher entropy than diatomic bromine liquid? Most important factor in predicting entropy is state of matter. Gases have higher entropies than liquids because there's more possible arrangements for them. So the entropy of a gas, always higher than the entropy of a liquid. Why does gaseous chlorine have a higher entropy than gaseous fluorine? They both have the same state of matter, but chlorine molecules weigh more than fluorine molecules, so the entropy is higher for a molecule that has a larger mass. How come C3H8 gas has a higher entropy than C2H6 gas? Just like the previous example, they both are gases, so it's not that reason, but these gases have different masses. C3H8 would have a larger mass than C2H6, and larger masses have higher entropies, so that's why C3H8 would have to have the higher entropy of the two. Why does the diatomic molecule carbon monoxide have a higher entropy than diatomic nitrogen? It's not that they're different states, they're both gases, and it's not that they're different masses, they actually both have the exact same mass, 28 AMUs. What's the difference? The carbon monoxide molecule is composed of two elements, where the nitrogen molecule is composed of only one element, and so the entropy is higher for more internal complexity, which means more elements making up the molecules. So we've talked about first law of thermodynamics, which was a review from Chem 1A. We introduced the second law of thermodynamics to you, and now we're going to finish up today by talking about the third law of thermodynamics, which states that the entropy of a perfect crystal at 0 Kelvin is 0. Now, what does 0 Kelvin mean? That means that molecular motion is stopped. Molecules are always undergoing some type of vibrational or rolling motion as long as they're at a temperature above the lowest possible temperature of 0 Kelvin. When you get to 0 Kelvin, the molecules stop moving. And if we take a look at a crystal of carbon monoxide at 0 Kelvin, it might look like this. And I would say this is a perfect crystal compared to this one, which is not a perfect crystal. Can you see why I would say that? You see the little flaw in that right crystal? It's colored in yellow right there. Oh, that CO molecule got put in backwards, okay? Well, the crystal to the right is imperfect. It will have an entropy that's greater than 0. But the one on the left is a perfect crystal. Its entropy has to be 0. Think about what its W value is. If you have, what are these, 16 different carbon monoxide molecules, they're all identical, then there's only one arrangement for them. W would be 1. So what's going to be the entropy? It's going to be 1.38 times 10 to the minus 23rd joules per Kelvin, multiplied by the log of 1. And what's the log of 1 equal? 0. So therefore, Boltzmann constant times 0 would give you an entropy value of 0. Now, for the imperfect crystal, that one imperfect carbon monoxide molecule that's backwards, well, that could actually be in any one of the 16 different spots. So therefore, W would technically be 16 for this. And so its entropy value would be Boltzmann's constant multiplied by the log of 16. Well, that comes out still a small number, 1.66 times 10 to the minus 23rd joules per Kelvin, but it's not 0. So the only thing that can have a 0 entropy is a perfectly aligned crystal in which the molecules are not vibrating, so they can't go into any higher energy states. They'll only have a W value of 1, so their entropy will be 0. Any non-perfect crystal or anything that goes up to 1 Kelvin or higher, it's going to wind up having multiple positions or multiple arrangements, and therefore will have an entropy greater than 0. So this is an important concept. Because of the third law, all substances that are greater than 0 Kelvin always have entropy values that are greater than 0. We're going to wind up looking at our thermodynamic table on handout 5, and now we're going to start using the entropy values that are given there. And when you scan through that, you're going to notice those entropy values are all positive. Why is that? It's because of the third law of thermodynamics. And these entropy values we're going to find on handout 5, we're going to use to calculate numerical values for entropy changes for chemical reactions. So third law entropies of 1 mole of many substances in their standard states at 298 Kelvin, and that's abbreviated usually S naught, are found on handout 5. So here's an example of handout 5. We've already talked about the first column. That's the standard enthalpy change of formation of each of these different substances. But now if we look at the last column, that's an entropy value. So let me pick one number on here, the bottom number for beryllium hydroxide solid. The standard enthalpy of formation is negative 904. What does that mean? From earlier today, that's the amount of heat that's released because it's negative when you form 1 mole of beryllium hydroxide from the elements that make it up, which means beryllium plus oxygen plus hydrogen. So that value is the energy change, the amount of heat that's released when 1 mole of beryllium reacts with 1 mole of diatomic oxygen plus 1 mole of diatomic hydrogen to form 1 mole of beryllium hydroxide. All those standard heat of formations have essentially that meaning. Okay? Now, what's this value mean? This 47, is this the entropy change when beryllium and oxygen and hydrogen form beryllium hydroxide? And the answer is no, because the symbol at the top of that column is not delta S, not sub F. It's not the entropy change of a formation reaction. This is incorrect. It's the absolute entropy of 1 mole of beryllium hydroxide calculated from the Boltzmann equation. So you need to understand when you're dealing with entropies in the thermodynamic table, these S values are not change in entropies of formation. They're absolute entropies, and these are calculated from the Boltzmann equation. So they're entropy values that are absolute entropies calculated from the Boltzmann equation for 1 mole of each of the substances in this particular table. And as I said before, if you look at this part of the table here, all the S naught values are positive, and that's because all entropy values at temperatures greater than 0 Kelvin have to be positive numbers. Now, if we have a chemical reaction occur and we want to calculate what the change in entropy is, we're going to be able to use these entropy values just like we used the standard enthalpy of formations earlier today. So for a chemical reaction, a change in standard entropy at 298 can be calculated from handout 5, and the way we're going to do that is the change in entropy of a reaction in its standard state will be the sum of the standard entropies of the products minus the sum of the standard entropy of the reactants. It's calculated just like we had done earlier when we were calculating enthalpy changes of chemical reactions. Let's try an example. Let's calculate the standard entropy change at 298 for the reaction 2 NiS solid plus 3 O2 gas yields 2 SO2 gas plus 2 NiO solid. So we're going to go to our thermodynamic table on handout 5, and we're going to go to the entropy values and look up each of the reactants and products, and we're going to go products minus reactants. So starting on the product side, there's sulfur dioxide, there's 2 moles of it, so I'm going to go 2 moles of SO2 multiplied by its absolute entropy of 248 joules per mole Kelvin. There's another product, so I'm going to go plus 2 moles of NiO multiplied by its absolute entropy of 38 joules per mole Kelvin. All the products are done. Now I go to the reactant side, I'm going to subtract these. Minus 2 moles of NiS multiplied by its absolute entropy of 53 joules per mole Kelvin, and minus 3 moles of oxygen, and notice this is not a 0 value, it actually has a greater than 0 value, the entropy of oxygen 205 joules per mole Kelvin. That's how we do that. In each of the terms, moles of each of the substances cancel out, so I'm going to be adding together joules per Kelvin plus joules per Kelvin minus joules per Kelvin minus joules per Kelvin. So my answer will be joules per Kelvin, and it comes out negative 149. So when you calculate the entropy change for reaction, the sign of the answer is what's important. If the sign comes out negative, that means that the system is becoming more ordered. So delta S predicts whether a system becomes more ordered or disordered. And because this is a negative number, this says the system is becoming more ordered. If delta S is ever a positive number, that means the system is becoming more disordered. Okay. And let's finish and see if we can just make some predictions generically. See if we can predict what delta S would be for chemical changes. Now, if a reaction becomes more disordered, that's when the entropy change will be positive because you're increasing entropy. So the entropy change is positive for reactions. Let's think about what might become more disordered. Well, in a chemical reaction, if you produce more gaseous products than the reactants, that's causing a greater amount of disorder. These types of reactions will have positive entropy changes. If you ever take a solid reactant, you dissolve it in water, you're now dispersing it throughout the liquid, you're causing the solid to be more disordered, that would cause an increase in entropy. So with these two little hints here, this can often be used to make predictions for entropy changes of reaction. Let's try a few to finish up. Let's say calcium carbonate is turning into calcium oxide and carbon dioxide. Would you think that the entropy change for this reaction would be positive or negative? Well, if we look at the number of gaseous reactants and products, there's no gaseous reactant molecules, but there's one gaseous product molecule. We're going from 0 gases to 1 gas. If you increase the amount of gas going from reactants to products, that's becoming more disordered. The entropy change is going to be positive. What if we have silver ions that are dissolved plus chloride ions that are dissolved and they form a precipitate of AgCl? Is that becoming more disordered or more organized? Well, if you make separate ions have to stick together, you're making them become more ordered. So dissolved ions, when they precipitate, become more organized or more ordered. That means the entropy change for that process would be negative. For this reaction, 2SO2 gas plus O2 gas goes to 2SO3 gas, delta S positive or negative. In this case, you're going from 3 gaseous molecules down to 2 gaseous molecules. You're causing the system to become more ordered. When you decrease the amount of gas, the delta S for this reaction would be negative. And then finally, what about a hydrogen ion with a bicarbonate ion turning into water and CO2? In this case, we have on the right side a gaseous molecule. On the left side, there are no gaseous molecules. So because you're increasing the amount of gaseous molecules in this reaction, we would predict the entropy change would be positive.